Good morning students, welcome back. We will start today symmetrical and asymmetrical networks. In these symmetrical and asymmetrical networks, we will study about the following things. The first thing is characteristic impedance and propagation constant for symmetrical T and pi networks, symmetrical T and pi networks. And second, we will study about the image and iterative impedances. And third, we will study about the image transfer constant and iterative transfer constant for asymmetrical L, T and pi networks. So here we will be studying about what is the characteristic impedance and propagation constant first, and then we will be applying for pi and T networks, symmetrical pi and T networks. Later image and iterative impedances we will be discussing about this one. So next is image transfer constant, iterative transfer constant with asymmetrical L, T and pi networks. We will also study here L network. So we will be seeing here about the characteristic impedance and propagation constant first of all. Before going to that, we will say about what is symmetrical and asymmetrical. Symmetrical in the sense which is having the input impedance and the output impedance same, is called a symmetrical two-port network. I again repeat, the symmetrical two-port network is the one which is having the same input impedance and output impedance. If Zi is equal to Z0, then it is called as a symmetrical two-port network. So here we will be dealing about the two-port networks. In the two-port networks, we will be seeing that how we will be deriving this characteristic constant and as well as this particular propagation constant. So now let's start that. Okay. A symmetrical network has two important properties. Symmetrical network has two important properties. One is characteristic impedance Z0 and propagation constant gamma. So characteristic impedance is given by Z0 and propagation constant is given by gamma here. Now we will see that what is a characteristic impedance. First of all, So before going to that, we will say what is a symmetrical network. In a symmetrical network, it has two properties important, that are characteristic impedance and propagation constant. And in this symmetrical network, if it is a symmetrical network, then what you have to do is you have to see that this particular network has symmetry on the input side and the output side. So for this we have to take into consideration two things. Suppose two networks are there. If two networks are identical, or if two networks are said to be identical, or they are saying to be a similar one, then if two networks are having the same characteristic impedance and as well as same propagation constant, then those two networks are said to be identical. Okay. Next, to find out this characteristic impedance, what we have to do is, first of all, you have to consider a cascade connection. You have to consider a cascade connection of the networks. Cascade connection means the networks are connected in a line. Like we are connecting a network, again the output of the network is connected to the input of the second network. Like that we can connect n number of networks. Okay. We will consider the cascade of the networks. Okay. Suppose this is one network and this is another network. Like this, another network also connected. Up to infinity. Up to infinity, we can connect these cascade networks. Okay. Now here we will be having impedance Z0. Suppose we are having the input impedance as Z0 here. Let this be represented by Z suffix 0. Like this, if you have the network connected in cascade, and if you are having this particular network starting from the second network, this network starting from the second network, let us assume this one like this. Infinity, up to infinity. Here what we have done here is we are starting from the second network. Here the first network is removed and we are starting from the second network. From a chain of networks, we are starting here from the second network now. So if we are starting from the second network, even though we are starting from second network, we will be having the input impedance as Z0. Input impedance as Z0. So if you are removing, now we are able to see here that we are taking out the first network here, and even if you are starting from the second network, even then the characteristic impedance Z0 is same, and Z0 is called as the input impedance, is also called as the characteristic impedance. Now if it is starting from second network, it is Z0. Even if you start from this third network also, it remains the same, Z0. Why? Because the networks are continuing up to infinity. The networks are continuing up to infinity. Therefore, we can say that if you are having this one, then this can be replaced by a Z0 only. So this chain can be replaced by Z0, because even you are cutting at third network, it remains the same. So you can write here Z0, and therefore you can say that the input impedance is also Z0. Input impedance is also Z0 here. Therefore we see that the output impedance, input and output impedance both remains as Z0 only. As here we see that it is being terminated here, and here after that it is being terminated here. So we can write this one as a impedance, characteristic impedance. If the characteristic impedance is Z0 at the input side, then output side also will be Z0, because even though you are cutting at any of the network, then it is remaining the same thing, Z0 only it is remaining. If you start from here also, the input impedance will be Z0 only. Like that, if you are having infinity, you can replace this by Z0. You can replace this one by Z0. So you are replacing this one by Z0, and this is called as the characteristic impedance. So if you see this figure, you can understand that Z0 is the characteristic impedance, and here we are disconnecting this network here, and even if you are disconnecting this network, all the networks still remain infinite only, these networks all together remain infinite. Now we can say that we are cutting at the characteristic impedance. Suppose you are cutting at the characteristic impedance here, then what happens? This input impedance or characteristic impedance will be continuing up to the infinity only. Now what can we do is, even though you are cutting at this network at those second or third or any other network, it remains still infinity. So what we do is, at this Z0, at this characteristic impedance, what we say that it is terminated at the Z0, it is characteristic impedance. So it is being disconnected at the characteristic impedance. So this characteristic impedance can be represented by Z0 here. The chain of the networks can be represented by Z0 itself. Why? Because even though you are cutting the one network or two networks, it is remaining Z0 only. So what we can do, the remaining network can be represented by Z0 here, and although this Z0 as the characteristic impedance remains the same, here Z0, and therefore we will be remaining part of the chain network can be represented by characteristic impedance itself. So here you can see that it is a symmetrical network where we are having Z0 as the input and Z0 as the output. So here the Z0 is called as the characteristic impedance. Okay. Now we will draw the circuit for this characteristic impedance. A proper network which is having 4 terminals. You can draw the network in this way, where you are representing this one as the characteristic impedance Z0 here, and here it is the input impedance Z0 and the characteristic impedance Z0. Okay, 2 terminal or 2 port network, or it is a 4 terminal network also you can write, 4 terminal network, because it is having here 4 terminals. This is 1 dash, and this is 2 dash. Okay, this is called corrected network. Corrected network or correctly terminated four terminal network. Here we can write the Z0 as a resistor, or you can write like this also, no problem. So this Z0 is called as the characteristic impedance. Z0 is called as characteristic impedance. Now you can understand that here Z0 was the input impedance, and after removing all this chain of networks, the impedance that was represented was Z0. Why? Because we were disconnecting each and every network, and still the input impedance was Z0, and therefore at the end of this up to we can't end up to infinity. So infinity, up to infinity, this characteristic impedance remains the same. If we are slowly cutting down one by one network also, even though we are cutting the input impedance or characteristic impedance was Z0 only. So if you cut like that number of networks also, the output impedance remains the same. So we can call it as a correctly terminated 4-terminal network. Instead of the chain of networks cutting off or disconnecting off one by one, we are writing here Z0. So Z0 will be called as the characteristic impedance, not the input impedance or output impedance. It is called as the characteristic impedance. For the discussion about the propagation constant, we are supposed to draw a cascade network like this. And as we are talking about the transmission lines, where which will be having the sending end and the receiving end. So in this networks, the transmission lines are considered as to be a 2-port network only, which is one side is considered as a sending end and other side is called as a receiving end. Like that, we are having here IS as a sending end, and this one I1 is the current that is the receiving end one for the second network, and here we are having the sending end I1 for the second network, and I2 is the receiving current for the third network here. Like that, these currents are being said here IS, I1, I2 and I3 and I4, but we see that the currents leaving the network will be of not same proportion as the IS here already. So IS and I1 will be different in phase as well as in magnitude also, because these are the AC quantities. We are having phase and magnitude here for the sending end and receiving end in the transmission lines. Now we will talk about what is the ratio of IS by I1. So IS by I1 is equals to, we represent e power gamma, that is e power gamma is equals to alpha plus j beta. Why? Because alpha plus j beta, here we are representing alpha as the real part and beta is the complex part, or we can say that here we are representing alpha plus j beta form, where the sending end and the receiving end will be calculated here, and therefore you are having here alpha plus j beta, where you will be having this j beta represented in the form of sin beta and cos beta, and alpha will be represented here e power alpha only. So we can write here e power alpha into e power j beta also is correct. So IS by I1 is equals to e power gamma, that is equals to e power alpha into e power j beta also. So this is the notation given for the ratio of the IS by I1. Now we will see how we will write this particular IS by I1 in the terms of this continuous propagation. So you are propagating this particular network like this. So we will write here IS by I1 is equals to I2 by I1. IS by I1 is equals to I2 by I1 also we can write here. So like this we can make I2 by I1 because this is the receiving end and this is the sending end for the second network. So we can write, instead of IS by I1 we can write I2 by I1 also. This ratio remains the same. Okay. So here IS by I1 is equals to I1 by I2 is equals to, you can write here I2 by I3 is equals to I3 by I4. Like that, IS by I2 is equals to IS by I2 is equals to, you can write here IS by I1, and we can write this particular thing as I1 by I2 and it is I2 by I3. You can write completely this particular things. Okay. Here you can write e power gamma IS by I1 into I1 by I2, that is equals to, here this I1 by I2 is nothing but e power gamma, IS by I1 also e power gamma. So we can write e power gamma into e power gamma, that is equals to e power 2 gamma. So if you want to write IS by I3, then it is Is by I1 into I1 by I2 into I2 by I3. Therefore, it is nothing but e power gamma into e power gamma into e power gamma, that is equals to e power 3 gamma. Like this, we are writing this e power 3 gamma and e power 2 gamma and e power gamma here. Okay. So we can write here Is by Ir is equals to e power n gamma for identical sections. Like we are having cascade connections, identical sections, we can write e power n gamma for n identical sections. Later, input current is represented by Is by Ir is equals to e power alpha plus j beta. That is equals to, if you see that this ratio is given e power alpha plus j beta, that is equals to e power n alpha into e power j n beta. Now what we do is here, we will write this j n beta in the form of this cos and sine, cos n beta plus j sin n beta, this particular thing. Later we write this rectangular form into polar form. Rectangular form into polar form, as you know that how to convert it, right off the square root of cos square n beta plus sin square n beta, just like square root of x square plus y square, square root of cos square n beta plus sin square n beta, and tan inverse of sin n beta by cos n beta, tan inverse of sin n beta by cos n beta here. So if you got like this, Is by Ir is equals to e power n alpha into at the angle n beta, because this is the polar form. We are having the here the polar form, and n alpha is given by magnitude and n beta is given the angle of two currents. So these are two currents are there, Is and Ir. So these two currents are should be how, in which phase, and what is the angle between, what is the magnitude and what is the angle will given by n alpha and n beta here. So Is by Ir is equals to, we can write Is by R into Z0 by Z0. That is nothing but dividing and numerator and denominator by Z0 only. So we can see that here Is into Z0 is nothing but Es and Ir into Z0 is nothing but Er. As we are having the Z0 common here, we can write Es and Er. Suppose you see here Es and Er is there, that is equals to Es by Er is equals to e power n alpha n gamma. E power n gamma nothing but, you can write here e power n gamma is equals to e power n gamma n alpha into angle of n beta. As we have said here that Is by Ir nothing but here, that we can write here in the place of Is by Ir, if you multiply Z0 by Z0, then you get Es by Er only. So we can write Es by Er. Why? Because if Z0 by Z0 is multiplied and divided, what it is, there is no change here. So we can write Es by Er. So Es by Er is equals to e power n alpha, voltage. E is voltage and here E is the receiving end voltage and sending end voltage, e power n alpha and n beta. So here the real part is called as attenuation constant. This real part is called as attenuation constant, and you can write E alpha is equals to Is by Ir for n is equals to 1. E power alpha is equal to Is by Ir for n is equals to 1. Alpha is equals to, you can set E that side, it becomes logarithmic value, log of Is by Ir. And here n beta is nothing but the phase constant. N beta is called as the phase constant and n alpha is called as the attenuation constant. So we will see that n alpha is equals to, for n number of networks, n alpha is equals to logarithmic value of Is by Ir Neppers. So the unit is Nepper here for this attenuation constant. We can say that this n alpha is represented by Neppers. Okay. So in the propagation constant, we are having here gamma is divided into two things, that is one thing is the attenuation constant and the other is the phase constant, that is measured in the radians. So students, we will end the topic here. We have studied now about the propagation constant as well as the characteristic impedance. So we will go for next in the class about the symmetrical T network and pi network and discuss about this characteristic impedance and the propagation constant there. Thank you.